you have a very happy Easter, although this was Easter unlike any other Easters you've experienced, I guess. Um, and once again, I wish you a happy Easter. Actually, we're going to have Easter. Easter is not only a 1 day event, it's a 6 week. So we're in Easter season for 6 weeks. So most likely, while we have this online teaching, I guess Easter season will be going on. And it's customary to say, "The Lord is risen, Alleluia, Alleluia," and you're supposed to answer, "Truly, He is risen, Alleluia, Alleluia." So we'll try this like tomorrow. All right. So you have to answer back, "Truly, He is risen, Alleluia, Alleluia." All right. Okay. So let's start with any question regarding the homework. You had like two questions to work on. One was both of them was on the website. Yes, Stephen. Stephen,
Can we go over yeah, can we go over question 19 on page 241?
19. There was a probably you did like this is for tomorrow, I think.
Oh,
19 on page
wait,
what?
no, on page 241.
On page 241. That was April the 7th. That was a long time ago.
Yeah, it was like I'm not sure about it.
Okay, hold on a second here. Let me go and grab. Yes, Max.
So for the second question, right? So that's where you had the cart move three
Yeah.
to three times.
Yeah.
I did it right. I got the right works, except they were all positive because I made the cart go in the other direction. I think.
Yeah, that's fine. Yeah,
Okay,
yeah.
great.
It starts from the bottom and goes up.
Okay, yeah.
Okay,
So I did. Yeah. Okay.
yeah.
Gotcha.
So number was that 19? You said how much work is done on a 750 kilogram load of bricks? Is that this one, Stephen? Is that the one, Stephen?
Yes, it is for
How
him.
much work is done on a 750 kilogram load of bricks by a bricklayer if you carry the bricks upward to a height of 8.2 meter to repair the chimney? Well, the minimum work that you can do to lift something. So if I have something right here, let me go back to let me see my own camera. All right. So in order to lift this up, the minimum force I need to require is at the very least, I have to apply the force that is equal to, well, a little bit more, but at least equal to the weight. Right. So whenever they ask you like, what's the work done in order to lift something, or how much work is needed to be applied, right, to do this, and this, they always sort of assume here what is the minimum work required. Okay. So in this case here, you're asked like to find like the work required to lift a certain amount of bricks over a certain distance. So the work done by you will be equal to the applied force, which in this case, the applied force is going to be equal to your weight. All right. Times, of course, the displacement, which is 8.2 meter, times cos of the angle between the applied force and the direction, which is cos of 0. Okay. So basically, let me sort of share my screen here a second here. All right, so basically here, so you have your mass of brick, and then so this is your weight, Fg, and you applied a certain force, and of course the minimal force that you need to apply must be equal to the force of gravity. Of course, it's going to be a little bit more, but virtually. And then you have your displacement right here. Okay, and that's it. So the work done by you is just going to be equal F8 times delta D times cos of the angle. So the angle between the applied force and the displacement is 0. So it's going to be 0 degrees. And this is going to be equal to mg times delta D. That's it. Is that okay, Stephen? Are you good?
Yeah, thank you.
Yeah. Okay. Any other questions? Okay, so let's start. All right, so today it's going to be like a little long here. The homework is mostly what you've learned last Thursday, so on potential energy, gravitational potential energy. All right. So today, just take good notes because this is not in your textbook. Okay, it's not in a textbook. Okay, so far you've you know how to use the work energy theorem, and also for more complicated cases as well, like the one I gave you like on Thursday. All right, so you know how to work with this. Now let's have a little example here. So there'll be okay. So the title will be this. So conservative forces. All right, and the symbol here will be F with C. Okay, we're gonna sort of look at this. All right, so let's pretend here that we have a book. So that's a book right here. And let's say the mass of the book is 2 kilograms. And then you lift the book from a certain height to another height. So let's see here. All right. And the distance here, so from here to here, so let's say here it's going to be 9 plus, let me see here, I'm trying to sort of find something that will be like easy. 4 plus 21. Bah. Okay, I don't have anything in. Okay, so let's say it's 5 meter here. And this is 2 meter high. All right. So consider lifting a book. All right. Now let's say you do it like this way. So the first thing you do, is you bring it along aside. So you move it like this, and then you move it up. All right, and this, we're gonna call this path A. All right, so you bring it across. Okay, Luke. So you bring it across first, and then you lift it up. All right, so let's find the work done by gravity. The work done by gravity. So work, whoops. All right, so work done by gravity. If you were in class, I would have put you into groups and then ask you like to find this and so on, but we cannot do it. So work done by gravity. All right, so along of path A. All right, so let's look at this here. So the work done by gravity along path A. So it's only the work done by gravity, guys. I'm not, all right, so let me see here. Okay, only the work done by gravity. So remember here, of course, that gravity will always be down, all right? Okay, so here you can certainly break it into two parts. The work done by gravity along the horizontal plus the work done by gravity along the vertical. Now, can anyone tell me what is going to be the work done by gravity along the horizontal section? Yeah, Max.
0 because along the x direction it doesn't move in the y direction.
Yeah, because the gravitational force and
Perpendicular.
the displacement at 90 degrees perpendicular to each other, so it's going to be 0, all right? So the work done by gravity is going to be only the work done by gravity along the vertical, right? So as we move it, like, whoops. All right, so this is the work done by gravity here. Now I'll put it on the other side. Right. So it's going to be only the work done by gravity along the vertical. So it's going to be like Fg times delta D times cos. Now, for this one here, so if I do the FBD here, so I do my little FBD, not the whole FBD, but if I do like gravity is down, and of course, the direction is up. So the angle between the two will be, of course, 180. All right, so that'll be like 180. And so this is equal to mg times delta D here times -1. So if we put the values here, it's going to be 2 kilogram, right, times 10 meter per second square, times, of course, 2 meter, and it'll be like a negative, right? So the work done by gravity will be negative. All right, so if we find this, you find that the work done by gravity will be equal to -40 joule, right? Now, instead of bringing it across first and then moving it up, let's pretend here that we are bringing it up by 2 meter and across. All right, so let me sort of use this here. So let's do this here instead. So we move it up first and then across. And this is going to be path B. All right. That's going to be path B. Now, if we do along path B, if I ask you what is the work done by gravity, well, you can see here the work done by gravity will be only along the vertical right here. As you go from here to here, here it's going to be 0, and you're going to get the same answer, right? So everyone agrees with that. You're all going to get the same answer, right? Now let's choose another path. So let's go from here to here in diagonal. And that's going to be path C. So once again here, this is my book here, FG here. So what I do here is I go diagonal. right? So I bring it from here to here, and I'm asking what is the work done by gravity. All right, so the same thing here, but now it's going to be along path C. All right, so now it's going to be a little bit more difficult here. So let's do a partial FBD here. So this is FG. And this is going to be delta D here, right? Now we know that the X component here will be 5 meters, and we know this is going to be 2 meters, right? And here, this is the angle. Actually, I'm going to call it something else. Sorry, guys. I'll call it alpha. All right, so let's look at this here. So the work done by gravity is going to be this. So it's going to be this equal to Fg times delta D times cos of theta. Now, what is theta? Well, theta is this angle, right? So everyone agrees here, theta is always the angle between the force and the displacement. Ugh. That's something a bit nicer. There you go. That's better. All right. Okay. Now I can write it as such. I can write delta theta is going to be equal to 90 degrees plus this. Everyone agrees with that? All right. So it's 90 degrees plus alpha. So if I continue with this one is going to be equal to mg times delta d times cos of 90 degrees plus alpha. There you go. You make this a little bit, add more space. I didn't know that. There you go. So now I'm going to continue here. Now, does anyone remember when I shift something by 90 degrees, what do I get? Anyone? So, yeah, Madav. Madav?
Would it be the inverse wave?
No. What do you do like when you shift like the angle of 90 degrees, guys? Have you learned about trigonometric functions? Have you?
Yeah.
Yeah, okay. So, yeah, Day.
Would it be negative sign?
Yes, that's correct. It's negative sign. Very good. Yeah, just talk. Don't chat unless you want to. All right. So this one here is going to be equal to negative sine of this. All right. Now we're not going to use like a decimal. We're going to use the fractions to find this. So let me put like the negative in front. Now, if you look at this diagram here, first of all, delta D. What is delta D going to be equal to? Well, delta D, it's going to be Pythagorean theorem here. It's going to be equal to this. It's going to be equal to 5 squared plus 2 square meter, right? So give us 25, so 29, right? So this is the distance here. What is sine equal to? Well, sine is equal to the opposite side, which is 2 meter, divided by the hypotenuse, which is this, right? So now we're going to put this right here. So it's going to be 29 meter times 2 over root square 29. Yes, Ernest.
On the test, do you want us to show it like that, or can we just plug it into our calculator?
No, that's okay. That's fine. It's just because I don't want to be bothered with decimals. I want like an exact solution. So that's why I do it this way. Okay.
Okay.
I don't care if you do like decimal or not. All right. Okay. So this, like, of course, like disappear. And then what we're left with this. So minus 2 kilogram times 10 meter times 2, the meter per second square. There we go. Times 2 meter. And what do we get? Well, look at that here. We get the exact same answer. The exact same answer as along the 2 other paths. Path A, path B, path C. So although I've done this only with 3 cases, if I had asked you, what is the work done by gravity if I bring this book from here towards this path? All right, so it's called this path D. All right, so instead of going like this, all right. Now, if I ask you like the work done along path D, well, what do you think the answer would be? What do you think the answer would be, guys? Yeah, Dewey. Yeah, Dave.
Negative 40 joules still.
Yeah, negative 40 joule. Exactly. Leo, yeah, you're right, too. Well, I don't know if you wanted to say that, but. All right, now, if I had given you this path here, path D, what would be difficult here? If I ask you like, all right, so find from first principle for definition of work, find the work done by gravity along path D. What's difficult? Tell me what's difficult. What is so different from what you've been accustomed to doing so far? Yeah, Madav?
We don't have lines anymore and we can't make triangles.
Yeah, we don't have lines. It's a curve. So therefore, what will happen? If we go back to the definition of work here, what do you think happened, guys? All right, if you go definition of work here. Yes, Stephen.
I mean, we can't really calculate the angle.
That's correct. The angle constantly change, right? So here, like, so right here, like gravity and the direction. So if you look at a little section, you would have to do like a little section at a time, right? You would have to look at a little section here. So this is like, don't write this down. This is like this. Gravity is down this way, right? And the angle is this. But as you go along here, the angle constantly change. So unless you know like the function, the function of this curve, and you know integration, you could do it, right? You could do it with integration. Okay, so let me admit this. Benjamin is not He was not here, Benjamin. All right, so unless you know integration, unless you know the function, you wouldn't be able to do that. All right, but you don't have to know that, because what happens here is that no matter what path you use, right, you're always going to get the same answer. So you choose something that is easy for you to compute. The key point here is that when the work done by a force is not dependent on the path being taken, when the work done by a force depends only on where you start and where you end up, we say that this force is conservative. So a conservative force is a force whose work is independent of the path linking the initial position to the final position. And that's very important because it makes our life way easier. Way easier. Okay? So let's do this here. So a force is said to be conservative when the work done by this force depends only on the initial configuration of the system all right, on the initial configuration of the system and the final configuration of the system. Depends only. So it means here, like example, initial and final position. Okay, example, initial and final shape of a spring. Okay, so we call this a conservative force. So work done by a conservative force is independent of the path linking the initial to the final configuration of the system. It's independent. Now, work done by conservative force I'm going to call this WC. So C, of course, refers to conservative. Okay, so don't write what I'm going to write right now. Okay, we're going to go this here. Don't write this down, guys. All right, just listen here. You're familiar with this symbolisms here, right? So let's see here, this. So F2, of course, will give you 8, right? So it's a function here. Now, I'm not so sure. Are you familiar with multivariable function? Are you?
No.
No, it's nothing else. It's just like instead of having only one argument, you have more than more than one argument. So that could be one here, right? So if I give I don't know 1 and 2, so you just replace x by 1, right, and y by 2, right, and it gives you this. So these are called like multivariable function. Okay. So far you've been doing only this one argument, but you can have as many arguments as you want. All right. Okay. So going back to this. So what happens for the work done by conservative force? The work done by conservative force is a function of only the initial configuration and the final configuration. Okay. So what you need to do, you need to know only the initial configuration, the initial position, and the final position of your object, and that's it for gravity. All right, you don't need to know like how you went from the initial position to the final position. Okay. Now this function.
Sir.
Yeah.
So for the homework problems that we did on Thursday, as the one where it was like the big system, would those technically be conservative forces because they're always in one direction?
No, not necessarily. Okay. No. No. Let me continue here. Okay. So this function is called the potential energy function. So this function is called potential energy. And the relationship is as follows. The work done by conservative force is equal to the negative of the change in potential energy associated with this force. I'll explain a little bit like later on why physicists chose like negative here. Why do we have a change in potential energy? Because I told you before that the only thing that we can measure is differences in potential energy. Remember this, right? Potential energy by itself has no really meaning. Okay, the only thing that we can measure, physically measure, is differences in potential energy. So that's why you have the potential energy right here, the difference. Okay. So let's do an example here. So let's see if this formula works for. Oh, by the way, so example of example of conservative force. Well, we found out one. One was the gravity. Okay, so gravity. Gravity is indeed a conservative force. The associated potential for any conservative force, there is an associated potential energy function. In this case here, it's called, of course, the gravitational potential energy, right? And right, it's equal to this. This is not the real one. The real one is the big one that I gave you like before, but for our purposes, for grade 11, that's going to be good enough. All right. Another conservative force. Another conservative force. I'll come back to this. Just ignore it. Another conservative force. Let me see here. Put this here. Close. All right. Another conservative force would be the spring force. Let's say here, this is the initial extension, initial configuration, initial shape of the spring. And let's say here that when I stretch it like this, it's the final spring. You have John Bell, Mandav. That's good. All right. Anyway, so this is the initial shape of the spring. This is the final shape of the spring. Now, if I keep track of the work done by me or the work done by the spring, right, as I extend it from its initial shape to the final shape, I'm going to get a certain value. So let's say the value is 10 joule. All right. So let's say I'm doing like 10 joule of work in order to extend this from this to that. Well, the spring force, as long as it follows Hooke's law, the spring force is a conservative force. What does that mean here? It means the work done by me or the work done by the spring depends only on the initial configuration of the spring and the final shape of the spring. So if I start with the same initial extension of the spring, and then I pull it a lot more, all right? And then I go back to the final shape, right? If I keep track of how much work I've done, I'm going to find out that the work will be exactly the same, right? It will be 10 joule. Whether you go from here to here directly or from here to there, all right? What matters is the initial shape of the spring and the final shape of the spring. How you went from the initial shape of the spring to the final shape of the spring is not important. So the spring force is a conservative force. Okay, the work done by a spring force depends only on the initial and the final shape of the spring. So that means that associated with a spring force, you have an associated potential energy that we call, of course, the elastic potential energy. So spring force, and then you have this one, right? So the spring force is a conservative force. Well, within the regime of Hooke's law. If you go beyond Hooke's law, it's no longer true. All right. Another force that is also conservative is the electric force. So the electric force is also a conservative force. And you have associated with it the potential energy that we call the electric potential energy. Right, which is UE. And next year we're gonna study this. All right. Another one is the magnetic. The magnetic force is also a conservative force. So what do you have? You have associated with this a potential energy that we call magnetic potential energy. Now, very often, like very often they drop potential. They say electrical energy, but it means electric potential energy. Magnetic energy, they mean a magnetic potential energy. All right, which is UM. So I'm not going to give you like the formula here. You'll never learn this anyway in grade in high school. So you'll learn this in universities if you go in the proper program here. Another one here will be the nuclear force. Nuclear force is also a conservative force. So we have associated with this a potential energy function that we call, well, of course, nuclear potential energy, nuclear energy. All right, and so on and so on. So whenever you have a conservative force, there's always an associated potential energy function all the time. All right, so let's see here if what we remember here, if we go back to this, remember we found out it was like minus 40 joule. Remember this? So it's a little laggy here. It's getting there. There we go. So we found out it was like minus 40 joule. All right, so now what we're going to do is we're going to apply this formula right here. Okay, it's coming, a little laggy. There we go, coming. So we're going to use this formula here. If we use this formula, it should sort of be able to give us the same answer. So let's find this out. All right, so oops. According to our formula, the work done by gravity is equal to this. Now, this is equal to what? This is equal to initial gravitational potential energy minus the final gravitational potential energy, right? The negative sign here will sort of switch. It's not like, it's not UF minus UI, but it's UI minus UF. Now we know what this is equal to. This is equal to MGHI minus MGHF. So this is equal to that. And if we use the reference, if we use the reference height as the, so if, yeah, it's going there here. So if we use the reference height as here, so you can see here that HI will be equal to 0 and HF will be equal to plus 2 meters, right? So we're going to use this here. So that's going to be equal to M. Let me put the value here. So it was like 2 kilogram times 10 meter per second square. It'll be like 0 meter minus 2 meter. And lo and behold, well, yeah, we get the same value, right? So that works. Okay. So gravity is a little special here as far as this approximation is concerned, as far as this is true here, right? The work done by gravity depend not only on where you start and where you end up, but depends only on the difference in height. Like the horizontal component, not important. Depends only on the difference in height. That's all what matters. Okay. All right. So questions? All right. Well, if there are forces that are deemed to be conservative, I get yes, Madav.
What makes a force conservative versus not conservative?
Well, just wait, okay? That'll take us like a little bit of field. You're not going to get an answer in grade 11, but anyway. So if their forces are conservative, therefore there are some forces that are non-conservative, and they're called non-conservative force. So non-conservative forces. So this will be like NC. So this is my N here, so get used to it. You should know that already. This is an N, like no. Okay, not a M, like mother, N. So non-conservative force. Well, what do you think a non-conservative force is? I don't want you to give me an example. What do you think like non-conservative forces are? If you know what a conservative force is, what do you think a non-conservative force will be? Yeah, they?
Its work done is dependent on the path you take.
That's correct. A non-conservative force is a force whose work depends on the path taken, not only the initial and the final position. Now, once again, I'm going to go through this here. Don't write this down. It's not very important. So let's say here that, you have a big block, a big, I don't know, a bookshelf of some sort. We're looking at it from the top, and you want to move it from here to there. All right, so from here to there by pushing it. Now, of course, you do this across a floor that is not frictionless. So let's say here you have two paths, path A and then path B. Now, if I ask you here, like, which one will be easier for you to push, like A or B? It's not really difficult. Leo?
Path A.
Yeah, path A, right? The work done by friction here, the absolute value, all right? So the work done by friction, of course, will be negative here. The work done by friction here will be less for A than it would be for B, all right? Now, notice here that you start for both paths, you start the same initial position, you end up at the same final position, and yet the work done by friction will not be the same. It will depend on the path taken, right? So friction is an example of a non-conservative force. All right, so let's go back to that. So let's put the so a non-conservative force. So a force is said to be non-conservative, Let me see here. This is like, yeah. A force is said to be non-conservative if the work done by this force and depends on the path. So depends on the path. Linking the initial to the final configuration of system. So it depends on the path. And so work done by non-conservative force I will call this WNC. All right. So WC is the work done by conservative force, and this is the work done by non-conservative force. It's important. There is no potential energy associated with a non-conservative force. All right. So whether for conservative force is always an associated potential energy, for a non-conservative force, there's no such potential energy associated with this. So it means that there's no frictional energy. There's no such thing as frictional energy. All right, so we're going to look at 3 examples of non-conservative force. That's it. There are more, but okay. So example of non-conservative force. Well, one was friction. The other one will be tension. All right, so there's no tensional energy. I'll put this in bracket because anyway. And the last one is an applied force. By a complex machine. Such as a living thing. Or a robot. Okay. So these are the 3 ones that we're going to consider as non-conservative. Friction is the big one. The other one is tension, and the other one is FA, so applied force. By complex machines such as a dog, such as an amoeba, such as a human being, such as a robot. These are non-conservative forces. All right. So now what we're going to do here, we're going to sort of I will sort of tackle something general. It's not like the best that we could do, but in grade 12, we'll flesh it out. We'll make it like a little bit more robust, more solid. For now, that will do for grade 11, okay? So there's a title here, but I'm not gonna put the title yet. All right, so but there'll be a title. So give some space here because I would sort of give up the punchline if I were to put the title. So there'll be a title. So we'll be like very general here. So consider a mass M subjected to various forces. All right. So we'll do the first one, and then tomorrow we'll do a case B. So for case A, it's going to be only conservative forces present. All right. So we have only conservative forces that are present here. So let's do an example here. Let's say here you have a roller coaster. All right, it's a roller coaster. And then so you have a cart here, your little car. All right. So let's look at this car here that is moving here. Whoops, I put like coast, forgot the coaster. There we go. Now we're going to neglect like friction. I know there's friction in this problem. We're going to neglect friction here. All right, so no friction this problem. What are the forces acting on this cart? Well, you have gravity. All right. And what would be another force acting on this cart if we neglect friction of any sort?
Normal force.
Yeah, normal force. Right? Right? So this is an example here. Now, if I were to ask you to compute like the work done by gravity from here to here, what would be difficult again? Yes, Stephen?
Yeah, since it's like curvy.
Yeah.
Closer.
Yeah, the angle constantly change. However, you don't need to know like the path here because the work done by gravity depends only on where you start and where you end up, right? Okay, so if you have like, so consider an object, right, of mass m, so like our cart here, you have only conservative forces present, all right? So using so let's look at the work. All right. So the work, yeah. So the net work The net work on the object is the work done by all the forces. You remember this. Now, what I'm going to do here is I'm going to group together all the work done by conservative forces, right? All the work done by non-conservative force. Okay, I'm going to put them together here. So I'm grouping them. Now, since we have only conservative forces present, well, this one here is 0, right? Because we consider only conservative forces are present. So what I've done here, I've grouped all the work done by conservative forces, all the work done by non-conservative forces. And then, of course, this is 0 here because there's only conservative force. So, whoops. So for this case, the network is only the work done by conservative forces. All right. Now, what do we know about conservative forces? We know that the work done by conservative forces depends only on the initial and final configuration of the system. So remember here that we can replace this by this. All right. So where U is the total potential energy of the system. Now, if there's gravity, well, you're going to put like UG. Now, if this cart here, like if there was a spring attached to the cart as it goes around, then it would also be potential energy. Spring potential energy. All right. If this card were charged and there were like some positive plate, negative plate, it will also be subjected to electrical forces. So you would put like the electrical potential and so on and so on and so on. So this is the total potential energy of the system. Okay. Now, using the work energy theorem, so remember that the work energy theorem tells you that the net work is equal to the change in kinetic energy of an object, right? Now, if I call this like equation 1 and this one equation 2, then comparing 1 and 2, what do we get? We get this. Okay, so I'll come back to this. Don't write this down here. If I have something that says this, what does that mean here? It means that if x goes up by 1, not by a factor, okay? If x goes up by 1, so does y, right? That's what it means, right? If x goes up by 2, so does y. Now, if I put something like this, what does that mean? Okay, I've got only Day. Anyone else? Okay, Day.
So if x goes up by 1, then y would go down by 1.
That's correct. So if x goes up by 1, y goes down by 1. Or if x goes down by 2, y goes up by 2. All right. So whatever gain there is in x, it's offset by a loss in y and vice versa. All right. So let's go back to this here. when there's only conservative forces present. Remember, that's our only conservative forces present. What does this equation tells you? What does this equation tells you? Okay, I have Madav. Anyone else? Okay, Madav.
As the kinetic energy increases, the potential energy decreases.
Yeah, okay, so your audio is a little bit like have problems here. Okay, so this is what it means here, guys. If there's only conservative force, as this car like goes down, what it does is it gains kinetic energy. But since there's only conservative forces present here, like this gain in kinetic energy will be offset by a loss of potential energy. In this case here, the loss of potential energy is the loss in gravitational potential energy. This object is losing height. So it loses gravitational potential energy and gains kinetic energy. All right? That's what it is. All right, so this is what it means when there's only conservative force. Now I'm going to sort of put this in a different form, and then we'll call it, we'll quit. So what I'm going to put here, I'll put this like Kf minus Ki is equal to Ui. Yeah, I cannot hear. Over UF. Now what I'm going to do here is I'm going to bring this term, the final and kinetic energy together. And I'm going to have this. And what I'm going to call this here, I'm going to call this mechanical energy. Called total mechanical energy. And total mechanical energy is the kinetic energy plus potential energy. Plus potential. Someone mute this. All right. So what does that mean here? It means that when there's only conservative forces present, it means that the mechanical energy stays the same. And whenever something stays the same with time, we say that it is conserved.
Wait, is that a U or an M?
No, that's M. That's a fancy M. Mechanical energy. It's a fancy M. All right. Okay. If you want, you can give a capital M. I don't really care, but I give like a fancy M. All right. All right. So what it says here, it says that whenever, whenever there is only conservative force, there's something here in the system that we call mechanical energy that will stay the same. All right, so all throughout this motion here, as the card goes down, the mechanical energy stays the same. And when something stays the same, we say it is conserved. So the title of this was Conservation of Mechanical Energy. There you go. All right. So we'll continue tomorrow. Today you have homework on what you've learned like previously on Thursday on potential energy. So that should be like fairly easy. And then tomorrow we're gonna sort of come back to this here. So I'll go over this like in greater details here, and I'll give examples here. Okay. Any questions? All right. So I'll see you tomorrow. Yeah, Ernest?
You scroll down, please.
Yeah, I will. You don't have to raise your hand 16,000 times. Max?
Wait, sorry. So is the extra hub session going to be?
I cannot hear.
Sorry. My mom's cooking in the background. So is the extra hub session going to be on?
I'll be on
Friday?
Fridays.
Okay. All right.
It'll
Thank
be
you.
like from 10 to 11. I'll tell you more about this.
All right. Cool. Thank you.
All right. So I'll see you like tomorrow at 10:30, and I'll remain on for perhaps like 5 minutes if you want to copy, if you have like questions to ask me. I will remain there for 5 minutes. Okay. Till then, I'll see you tomorrow.
Yes, sir.
Bye-bye.
Bye, sir.
Hi,
Bye.
sir.
Bye. Bye. Chat. Who wants to chat? Luke, you don't have to chat bye. Just say bye. It's fine.
Bye, sir.
Bye-bye.
Sir, can you go from the very